section 5 is the last section we're going to talk about in the chapter. It is about tangents, and tangents are any line, right, or line segment that lies outside of the circle and intersects the circle at exactly one point. Okay, so in this picture to the right here, point P is that what we call the point of tangency, where the tangent line intersects the circle, but line T is tangent to the circle. Okay, a couple theorems we're going to talk about. The first one is the tangent radius theorem, and it says that a line is tangent to a circle if and only if it is perpendicular to the radius that is drawn to the point of tangency. So in this picture here to the right, point T is the point of tangency. ST is a radius, which means that line L here is perpendicular because L is tangent to the circle at point T. Okay. Couple different kind of examples that we will focus on specifically. First one is determining if a line or a line segment is tangent to a circle. Okay, so for GH here to be tangent, we need to know that angle G is a right angle. Okay, so that's actually the question that we're asking ourselves. Okay, so if we look at, yikes, nope, that's not what I wanted. If we look at the triangle FGH, we're essentially going to determine, is this a right triangle? Okay, so we're going to use the converse of the Pythagorean theorem that we talked about in chapter 8. Is c squared, so is 12 squared equal to 6 squared plus 8 squared? Six squared is 36. What am I doing? 8 squared is 64. When we add those together, we get 100, but 12 squared is 144. So since angle G is not a right angle, GH is not tangent to the circle. Okay. The next kind of example, though, if we are trying to find a value of x, here we know BC is perpendicular to AC. All right, so since this is a radius drawn to a point of tangency, we're going to use the Pythagorean theorem to find a value of x. All right, 14 squared is 196. 17 squared is 289. When we subtract from both sides, our x value squared is 93. So we can say that x is the square root of 93, or about 9.6. All right. Example 2 is a little bit different, only in that this segment here, the whole thing is x plus 2, okay, because x is just this portion here, that radius. We can also put x here because all of the radii are congruent. So if you will try this example on your own now, angle Q is a right angle. Last theorem we're going to talk about is the intersecting tangents theorem. Down here we've got, nope, zoom back in. Nope. In this picture, we've got the segment AB and CB, both tangent to the circle, and they intersect at point B. Okay, when that happens, those segments are congruent. Okay. Couple different kinds of examples we're gonna focus on. This first one, we know AB and CB are tangent to the circle, so they are congruent since they intersect at point B. So we get to set 2x minus 5 equal to x plus 15 to find x. Subtract x from both sides, add 5. We get x to be 20. All right, try examples 2 and 3 on your own. We will talk about them in class if we need to. And then this last kind of example, when you see something that looks like this, where we've got the radii also included in this picture, okay? All of our radii are congruent. These tangents are congruent, okay, which means we are actually looking at a kite. Okay, so you might have to pull in some information from chapter 6 with properties of kites. But for now, we're going to do example 1 together. Okay, since AB is tangent to the circle, angle B here is a right angle. And we are going to focus on just the top part here, this top half of the kite, where we've got a right triangle. Okay, and if we know angle B is 90 degrees, angle C is 65 degrees, angle BAC is the third angle of that right triangle. So we just need to find the third angle. And that measure is 25 degrees. Okay, example 2 and 3 are very similar, so try those on your own, and then we will talk about them in class.